Y13, Ampere's law. Magnetic field is induced by a current I. The positive charge is moving upward. In that case, if there is a charge distribution, stationary charge distribution, then the electric field radiates along the parallel to the planar radius direction. This is the E field. However, if the charges are moving, sure, still there is an electric field because there are charged. In case we have negatively charged particles to cancel the whole amount of net charge, there is no electric field. And if only the electrons are moving backward, then the net electric field, according to relativity, there exists. But if we ignore the relativity, electric field is vanishing. Instead, because of the moving electrons, current I is going upward, and the magnetic field is induced. Magnetic field is induced by a current. And the strength of the magnetic direction of the magnetic field, according to this figure, you use your right hand then your fingers follow the directions. This is your thumb, and your fingers will follow the direction of the magnetic field induced by the current. The thumb is parallel to the current. And if you see this figure from upward, then you will find the current is flowing out and the magnetic field is rotating around the current. The strength of, so the direction is a tangent. This E phi represents the direction of the tangent. Magnitude of the magnetic field, there is a constant, mu zero, that is called the permeability constant. Strength is proportional to the current, and the strength decays. You should be familiar with this 2 pi rho. This is a rho, planar radius, and the circumference of the circle. This circumference is 2 pi rho. In the case of electric field, that decays is 4 pi epsilon 0 1 over r squared. 4 pi r squared is the surface area of a sphere of radius r, because it is being radiated in 3 dimensions. In this case, current is flowing along a single direction, then the problem reduces into the 2-dimensional problem. Sphere in 3D is truncated into a circle in 2D, and the surface 4 pi r squared in the case of electric field propagating in space from a point here, magnetic field propagates from this current. So this is 2-dimension. The surface area of the 2-dimension is nothing but the circumference of the circle. So structure of the magnetic field is like that. Biot-Savart law is the basic law to derive the magnetic field. It is a sum of the components induced by a small wire segment that constructs a circuit. We have chosen a simple circular circuit, and we have a current I flowing inside a circuit. This is the line segment of the circuit, infinitesimal, and I use the prime for source and unprimed one. This is field. We measured field at point P, and this point Q is the point at which a current element is distributed. It follows the inverse square law. This capital R is the magnitude of this vector. What is that? This is the displacement from the source to the field. So this length square is divided. And the magnetic field has the proportionality, the length of the line segment, and we have the direction of this line segment and direction of our vector. A unit vector is chosen ER hat. You use the right hand to find the cross product between this one and this one. The direction is this. You want to integrate over the whole circuit to find the induced magnetic field due to a circuit. Again, we have a proportional constant mu 0 I divided by 4 pi instead of 4 pi epsilon 0. Okay. Let us compute the magnetic field due to a current in a long straight wire. X prime, I told you this is a source point. Source of the current is distributed over this straight wire. Let us choose the z-axis. Then the x prime has a coordinate z, and its direction is E3 hat. Differential element of the displacement, this wire segment, is dx prime. We choose the field point. Field point is point P. Point P has been chosen like that, and there is an origin that is at the center, equal distance to both the ends. Okay. So the displacement from the source to the field point is a field point vector subtracted by the source point vector. E rho is a unit planar radial vector that does not have any z component. Therefore, the magnitude of this displacement is square root rho square plus d squared. If you look at this situation, you will find there is a right angle. Z is negative and rho, and this is a z squared plus rho squared, and z runs from minus something to plus something. Okay, according to Biot-Savart law, we have overall factor, distance cube, cross product between the y segment and the displacement vector. We substitute these results. Here, E3 cross product vanishes. E3, E rho is E5. Therefore, we have radius, planar radius rho and dz. Product appears here. And then we rescale this integral. It's a scaleless variable, z over rho. So, for example, we pull out rho and square root 1 plus z over rho squared, this one. Then it is 1 plus alpha squared. 1 plus alpha squared, and we have cube. Square root 1/2 and cube. And then this overall factor has been pulled out like that. Now, we want to evaluate this integral from minus infinity to plus infinity. Integral table can be used to find the answer. Substitute this one. If you at infinity, it becomes 1. At minus infinity, it becomes a minus 1. Therefore, 1 minus minus 1, that is 2. That factor of 2 removes factor of 2. Therefore, we end up with the result without calculation I told you, and we have reproduced this result using the Biot-Savart law. Magnetic field due to a circular current. We have a field point just above the center of a circle in which current I is flowing. We have a source at rho, and we have a field point P on the z-axis. Okay, so the displacement is ZE3 subtracted by source rho. Okay, and then according to Biot-Savart law, the numerator factor has this form. Substitute these into here, and differential of the circuit element is like that. Cross product, we have two components. Phi z equals rho. Rho phi is a z, so phi rho is a minus z. Therefore, it becomes a positive, and this is the answer for the numerator. And then we integrate over a circle. You will find this E rho hat has cosine phi E1 hat, sine phi E2 hat. And if you integrate over the angle, these two guys disappear. Absolutely. Because cosine phi, d phi 0 to pi equals 0, and sine phi is also 0. So we don't have to compute this. What about this? This is independent of angle. Independent of angle. Invariant under rotation. This z-axis is invariant. So if you integrate over phi, what you're going to do is just simply multiply by 2 pi. Okay, so as a result, your answer is, because of this 2 pi, 4 pi in the denominator, mu 0 multiplied by 2 pi. This cancels and factor of 2 appears in here. Remaining pieces are constants, and if we take the limit, z goes, okay, exact result is like that. Now, we would like to introduce magnetic dipole moment. Magnetic dipole moment is pi rho squared. This is area. Area multiplied by current. Area of the circuit, pi rho squared, multiplied by current. And the direction is a normal to this plane, but this orientation is either this or that, but use your right hand to find the direction of your thumb. That is the direction of the magnetic dipole moment. Using this relation, we can re-express this magnetic field when z is much larger than rho. Then it becomes like that. Next, the magnetic field here, we have ZQ. ZQ, you remember the electric field due to electric dipole? Electric field due to electric monopole decays according to radius, 1/4 radius squared. This is a monopole. If there are two poles, plus and minus, then it becomes a dipole, and the leading contribution cancels, and subleading contribution, that is proportional to 1/r cubed, survives. This is the electric field strength due to a dipole. Just like that, we have a z cube, z, this is rho radius is very tiny. We have a current, circular current, magnetic field is like that. And anyway, along this straight line, parallel to the magnetic dipole, the strength decays not by 1/4 distance squared, but by distance cubed. If you have additional turns, then the dipole will, magnitude of the dipole is linearly increased by a number of turns. Single turn, double turn, many turns, your dipole will be increasing. First, between two parallel currents. Suppose that we have a current I, then you will find that the magnetic field is rotating about this current. If there is a magnetic field and there is another current, positive electric charge will follow the direction of the current. And you know how to compute the force on a charged particle moving with the velocity v. V cross B multiplied by charge Q. That is the force. However, we have a continuous current. In that case, this one is a Q, length, time. If you take this one into account, this is the current and this is the length. And direction is the following the current and had something like that. Therefore, the magnetic force applied to a current should be of this form. V QV cross B should be replaced with I length, and then this cross B is common. We know how to compute the magnetic field due to this current according to the Biot-Savart law. The result is this. Substitute. Finally, you will find if the two currents are parallel, the force is attractive. In case the currents are flowing in opposite direction, they are repulsive. Okay? If you look at this figure from upward, current is flowing out, magnetic field. In between, the two fields cancel. They are opposite direction. So this becomes weaker. Therefore, the net magnetic field line is like that. That's the reason why they are attractive. If it is opposite, magnetic field coming out, in this case, they add up. If they are opposite, field lines becomes dense and their force is repulsive. Ampere's law. Ampere's law closed the path inside current I passes through, then along this counterclockwise direction, the magnetic field integrated over this closed path is proportional to permeability constant multiplied by I, and I is enclosed by this closed surface. We can replace this current with surface integral over S of the current density. And then we can replace this closed path integral as a curve and scalar product with the surface element due to the Stokes theorem. And this surface, okay, shrink this size of S, then you will find the differential form of the Ampere's law. if you take into account the current density instead of a thin current, wide area, the current is distributed over the wide area, then current density is current divided by area. And it is still a vector. It has the direction of the current or direction of the velocity of the drifting charge. So you substitute this current density and you will find the same result for the Ampere's law outside the thick wire. But inside the thick wire, then the amount of current enclosed by this small closed circuit, closed path, should be smaller by a factor of radius squared. This is current, this amount is current I, but the current surrounded by this Amperian loop is smaller. Solenoid use this Ampere's law many times. For example, we have a loop. Choose this loop, you will find current I flows out, but there are a number of turns, many turns, then amount of current passing through this closed path is proportional to the number of turns. Therefore, using this, the left-hand side integral is, we know the magnetic field is very strong inside, and magnetic field outside is almost vanishing. Therefore, magnetic field is concentrated inside the solenoid. So this integral is magnetic field multiplied by length. Okay? And right-hand side is known very well. Using this result, we can compute the magnetic field inside a solenoid like this. Just as I have explained, magnetic field is concentrated inside the solenoid. Toroid is similar. In that case, we choose Amperian loop, and this loop will enclose the same number of turns. Now, the magnetic field is concentrated inside, so the length, the BDL, this integral, has a magnitude of magnetic field multiplied by the circumference, so 2 pi rho appears in here. Previously, we have considered the field point just above the center of a circular wire carrying current, but we can also consider arbitrary point. Computation is a little bit complicated, but at the end of the day, it requires to evaluate the elliptic integral. However, we know how to simplify this using binomial theorem, binomial expansion that was not developed by mathematician, but developed by Newton. And following Newton's way, we can compute this integral order by order. The final result shows that previously, when we are just above the center, the magnetic field was very simple. Just above the center, it was like that. It directs single direction. However, this plot shows that it is rotating to return to the south pole. That figure is being generated by more accurate result obtained by using series expansion method developed by Newton. And this is the general form that is not accurate forever, but accurate to the subleading order for the magnetic field due to magnetic dipole.